Every day, tens of thousands of containers are unloaded in Europe's busiest ports. Millions of tons of freight, which will flood all over the continent. But the transport of all this cargo has always come up against an almost impassable barrier, situated in the very heart of Europe, the Alps. An obstacle finally overcome thanks to the construction of a brand new rail tunnel some 57 kilometers long, the longest tunnel ever to be built in the world. Dug beneath the São Gotardo Massif, this titanic miracle of engineering now allows freight trains to pass through the Alps at 160 kilometers per hour in barely 20 minutes. And passenger trains go even faster at 200 kilometers per hour.
It's as if we demolished the Alps.
Construction workers, engineers, surveyors. This enormous project mobilized 6,000 men and women for 20 years and required ultra-complex boring techniques.
We had to attack 5 points at the same time.
The Channel Tunnel is nothing next to this.
A colossal task carried out 24/7 in extreme conditions.
The rock gets very hot. When you touch it, it's at 50 degrees.
We're going to tell you how man achieved this crazy dream of defeating the biggest natural barrier in Europe.
This tunnel overcame countless challenges.
To bring this exceptional adventure to life, we met those who constructed this monumental tunnel. Civil engineers like Davide Fabri and Werner Kradolfer. Head surveyor Adrien Rief. Head of all rail engineering Nicola Steinman. And the CEO of the main construction company, Renzo Simoni. They'll share all the secrets and present the ultra-modern means that were needed to achieve this incredible feat. We'll also reveal the mind-boggling difficulties the engineers were faced with.
At some points in the tunnel, we measured wind speeds of up to 350 kilometers per hour.
Some of the terrifying incidents which threatened the site.
How did we get out? We had to dig a lateral tunnel going backwards and using explosives.
And the unrivaled safety measures which had to be deployed to prevent the dream from turning into a nightmare.
There's a risk of derailing, especially at speeds of over 200 kilometers per hour.
Between the start of the work and the inauguration of this record-breaking tunnel, 20 years of hard labor were necessary to finally make history.
Then we could finally announce it. We've done it. The 57-kilometer tunnel into the Alps has become a reality.
You'll see how in the 21st century this outsized tunnel has changed one of the main trade routes of the old continent forever. The Alps, Europe's highest mountain range, covering 60% of Switzerland. A natural barrier which for a long time held man back, until he had acquired the technology to break it. A symbol of our constant fight to tame nature, the São Gotardo Massif, situated in the very heart of the Alps.
Gotthard has always been a part of a Swiss legend. You can almost say Switzerland was born from this legend. But Gotthard was previously an obstacle and a source of danger. And over the centuries, we've managed to go over and under it by building transport links between north and south.
The gradual deployment of the Massif with more and more modern infrastructures has always been crucial to Switzerland. The roads which crisscross the Alps north to south, east to west, are the country's economic arteries. With over 25 million tons of merchandise in transit every year, It's even one of the most frequented trade routes in Europe.
Having thousands of trucks on their roads was pure hell for the Swiss.
The ecosystem needed to be protected, and the Swiss simply had to find a solution.
The Swiss transport authorities established the policy of transferring truck-hauled freight to rail freight. To do that, existing rail network capacities needed to be increased.
The aim of the policy was to protect alpine flora and fauna, but also the inhabitants, who were suffering from increasing noise and exhaust pollution. But developing rail freight in favor of road freight was a huge gamble. To convince a hauler to unload his goods onto a freight car only to reload them farther down the line would require big savings in both time and money.
A tunnel works for everything. Well, works for freight, also works for passengers. And they knew passenger transport would increase.
Switzerland's government already had the solution. In 1882, Swiss engineers had already bored a first rail tunnel under the São Gotardo Massif. Lying at an altitude of over 1,100 meters and 15 kilometers long, it was the largest tunnel ever constructed.
The first Gotthard rail tunnel broke all records back then. Today, 15 kilometers is nothing. But this was the late 19th century, and it was dug with pickaxes and sweat.
They used dynamite, recently invented by Nobel, so the Swiss used very recent, very innovative technology to bore the tunnel.
The tunnel started high up in the Massif and obliged trains to zigzag their way up at slow speeds. So the idea was, if the tunnel were bored at the base, it would be totally straight and ideal for high-speed trains.
The project was titanic. The chosen line would require boring through 57 kilometers of rock, the equivalent of crossing Paris 3 times from east to west.
This tunnel overcame countless challenges. It was an extraordinary sight and probably one of the most complex pieces of engineering in the world.
Especially as the engineers soon realized there would need to be 2 tunnels, one for each direction. With the addition of a junction between the 2 tubes every 325 meters, a total of 152 kilometers would have to be dug.
If I had put the rail tracks in both directions in a single tunnel, I'd have had a tube much too wide to support such geological conditions at such a depth. The wider the tube, the more fragile it is. So the problems multiplied, starting with the risk of the structure caving in on itself. So we went for a project with 2 tubes, with a reduced width, to reduce the risks.
Concretely, that would mean extracting 28 million tons of rock from the inside of the mountains, the equivalent of 5 great pyramids of Cheops. A figure that makes the head spin. And the second tunnel would be even harder to access, as it would pass at some 2,300 meters beneath the highest summit of the Massif.
At any given moment, any given element can become extremely dangerous.
And as difficulties often come in pairs, the engineers knew that they couldn't bore in a straight line. Some zones had to be bypassed to avoid causing a disaster.
You're passing through the Alps, so there's geological layer after geological layer, which is a real conundrum for the geologists and the engineer who wants to dig a tunnel there.
There are some parts of the massif where the rock is homogeneous, hard and solid, and others which are much trickier, where the rock has been modified and made fragile by the huge pressure from the mountain. In those areas, it's flakier, less resistant, and sometimes even pulverized.
The first question was, will we be able to probe? If so, what will we find? And will it be possible to bore through ground with so many layers?
Another difficulty was that the new tunnel would pass close to 3 hydroelectric dams. A nightmare for the technicians, when you know that water seepage is one of the worst dangers and could threaten the structure of a tunnel.
We knew we had to be careful because the dams were above or adjacent to the route, and there would be subsidence.
There was a risk of the dam giving way and causing a disaster.
For absolute safety's sake, we took ultra-precise measurements over 15 years.
Here's the tunnel constructed in 1882, since the aim of the new tunnel was to cross the São Gotardo Massif from one side to the other at the base of the mountain. It was named the Base Tunnel. Engineers, construction workers, surveyors, almost 6,000 men and women were mobilized every day on this mammoth site for 20 years. Work began in 1996. Step 1, to dig an 800-meter deep access shaft to enable the laborers to work in both directions of the tunnel.
From the outset, the whole team knew it would be a long-term job, that it would be extremely difficult, and that they were faced with a huge challenge.
They were also aware that they would be writing a new page in history, but there would be lots of hard work first. An outsized project like this would require exceptional machines, specially designed to meet this incredible challenge. The job of this machine was to bore through the mountain. Over 450 meters long, the equivalent of 4 football fields, this huge state-of-the-art cylinder is a tunnel boring machine, or a TBM.
It's hard to imagine the power and weight of this amazing machine. It weighs 3,000 tons. It's monumental, gigantic, simply awesome.
The head alone resumes the colossal power of the machine. With a diameter of 9.5 meters, the equivalent to a 3-story building, it's equipped with 58 cutting wheels. Each of them exerts a pressure of 32 tons on the rock, gradually pulverizing it as it turns. The pieces of crushed rock which are extracted are called chips.
The TBM has 2 parts. The head, with the cutting wheels that break up the rock as it bores through. And behind, the rest of the machine has grippers which push against the newly dug walls to provide very powerful forward thrust.
This steel monster produces 42,000 kilowatts of power and can extract up to 6,000 tons of rock each day. It's not a new concept. A similar TBM was used to dig the Channel Tunnel, but it was the first time one had been used on such an extreme site. This time, the stakes were even higher. So to meet the deadlines, without going above the 10 billion euro budget, the engineers decided to use not one, but several TBMs.
To dig such a long tunnel with reasonable deadlines, we had to attack 5 points at the same time and via a shaft some 800 meters deep.
There were 5 bids for tender won by 5 different consortiums. Each of them was attributed with a section where they had to work at the same time as the others.
But by deciding to split up the tunneling work, the engineers simply multiplied the risks of breakdowns and thus delays. And as you'll soon see, despite the thousands of hours of simulations and calculations, hazards on such a site are inevitable. Meanwhile, the consequence of this division of labor was the pressure placed on the shoulders of the surveyors.
The role of the surveyors was vital. As the tunnel was attacked at several points, the 2 tubes needed to come together with absolute precision.
The slightest error would have spelled disaster. We'd have done all that digging for nothing. So the surveyors stepped in with their measuring tools, mostly equipped with lasers, and took extremely precise measurements for the directions the TBMs needed to take.
The danger was very real. With each contractor working on its own section, how could the teams be certain that the 5 different stretches of the tunnel would be perfectly aligned at the end? The very slightest of offsets at the start of a stretch could result in a discrepancy of several meters at the other end. A disaster for such a huge project. So the surveyors were constantly on the alert. Their mission? To ensure that the route of the tunnel and the diameter of the borehole were strictly respected. The surveyors were equipped with 2 tools of formidable precision. The first was the tachyometer for measuring the angles and distances of the tube by projecting a laser beam onto the walls.
There are 2 very important instruments, the tachyometer for long tunnels and the gyroscope. The particular thing about long tunnels is you must regularly check the trajectory and adjust it every time, and that's what the gyroscope's for.
In expert hands, these 2 instruments would enable the surveyors not to exceed the accepted margin of error, a minuscule 25 centimeters, less than the height of a sheet of A4 paper, an amazing feat for a 57-kilometer-long tunnel. But the borehole was far from being the only headache that the project designers had to overcome. The other major challenge of this record-breaking tunnel was the strength of the structure. And in this area, the risks are directly proportional to the huge scale of the project.
Rule number 1 is, the moment you've finished boring a small section of tunnel, you immediately consolidate it so that it doesn't cave in.
Back to the early 2000s, the tunnel was advancing rapidly. As the TBMs continued to bore their way through the mountain in 2 directions, workers specialized in tunnel consolidation stepped in. To understand what was at stake during this next stage, you must bear in mind a simple principle: nature hates emptiness. Digging a cavity as deep as this, up to 2,300 meters deep, changes the balance of forces beneath the mountain. Rock tends to naturally cave in on itself to fill the void, the biggest fear of the engineers.
We had to consolidate the walls and roof without reducing the diameter required for the passing of a high-speed train. That was the big challenge. We had to find the right balance between strength and effectiveness, because the tunnel is planned to last for at least a century.
The technique had to be perfectly synchronized. The consolidation of the walls and roof had to advance at the same speed as the boring of the gallery. This was true regarding the safety of the crews, of course, but also for that of the entire edifice.
After boring, we had to cover the walls and roof with concrete to support the rock and prevent it from caving in on the TBM.
We added anchors in the rock to prevent any cracked blocks from falling. The layer of concrete was reinforced with extra strong mesh, which serves to rigidify the ensemble. If needed, we would add extra, thicker, longer, and more resistant anchors.
The anchors are huge bolts screwed as deeply as possible into the rock. But at more critical points, where the pressure was particularly high, there weren't enough to guarantee the safety of the tunnel.
The mountain was being deformed to such an extent, and the pressure was so strong that the underpinning alone wouldn't have provided enough resistance. So the trick was to allow a small amount of pressure exert itself so as to reduce its impact on the walls and roof. So the hull had to be able to deform slightly to absorb the pressure. That's the principle behind digging such a large tunnel.
This huge length of suspended steel, it's known as a flexible girder. As its name suggests, it's designed to deform under the effects of strong pressure. The idea was to place thousands of them around the wall's roof and floor at places most threatened by strong pressure, by joining them together one after the other to create steel strapping for the tube.
Once fixed together, the steel straps would slide to a stopping point. Then they began to slowly deform until we decided to block them at the stopping point.
By blocking the deformation of the steel straps, we created resistance around the tube. The biggest difficulty was finding the right stopping point and then stabilizing the steel straps. And always bearing in mind that over-deformation would modify the profile of the tunnel, which could then prevent trains from getting through.
Along with the hull and reinforced concrete, this strapping forms an indestructible shield around the tube. One major question remained. Where do you find hundreds of thousands of cubic meters of concrete needed to make the shield? Remember that each of the 4 TBMs used on the site can extract up to 6,000 cubic meters of rock every day, the famous chips, which turned out to be providential material for the engineers.
What do you do with 28 million tons of excavated rock? Imagine a 2-lane highway lined with concrete mixer trucks coming from the north of Europe down to the south, non-stop. Then they had a fantastic idea. They'd use a lot of the rock to make their own concrete for the tunnel surfaces.
In fact, the rock would serve as the base material for the production of the cement used in making reinforced concrete. That's why we installed giant crushing and grinding machines at the tunnel entrances. Once turned into concrete, the chips returned to where they came from, deep inside the tunnel.
Thanks to this ingenious technique, 40% of chips extracted from the gallery were recycled in order to make the walls and roof safe. The remaining 60% were dumped in old abandoned quarries. Several dozen cubic meters even made vacationers happy when it was used to build artificial islands at a Swiss lake resort. At this stage of the Titanic project, you might believe that the 2 57-kilometer-long tubes and their junctions were now completely out of danger. But that's without counting on one final threat, and probably the most dangerous of all, water seepage.
Water is enemy number 1 in tunneling because it can cause so much damage, so it's absolutely vital to prevent water seeping into the tunnel.
We needed to construct a totally waterproof tube, and we achieved this with a film that would coat the tube, making it completely waterproof.
The system is based on a plastic waterproof film that's only a few millimeters thick. We had a massive roll of the waterproof film, which we unrolled around the roof and walls, and then welded it together at certain predefined points.
Here is an animation of this famous waterproof film. Rainwater that constantly seeps down through the mountain collects on either side of the tunnel walls. If nothing is done to prevent this, here's what might happen. The pressure would continue to grow until the tunnel explodes under its weight. The solution? To lay at the base of the tube drainage pipes to evacuate the water towards the outside.
Drainage pipes were laid along the whole length of the tunnel floor to collect seepage and to gradually evacuate it to a central collector in the middle of each tube. This water is then redirected to the mouths of each tube.
Once collected, the water is left to flow back into nature. The natural seepage of water down through the mountain would actually be the cause of one of the biggest material accidents of this extraordinary construction site. Despite the number of probes carried out to test the quality of the rock, nasty surprises are inevitable over such a distance. In 2003, the boring of one of the stretches in the northern section brutally came to a halt.
The TBM advanced into a zone of soft rock, which crumbled as the cutting wheel came into contact with it. The rock collapsed and totally buried the machine.
Impossible to move it, impossible to reverse. Work could have been held up for months, years, or even been abandoned.
Over the centuries, water seepage from rain and melting snow had ended up totally damaging this vein of rock, which the probes had failed to detect.
The amazing idea they came up with was to build a bypass tunnel so they could reach the machine from the other side.
Once on the other side, we were able to clear the flakiest rock, consolidate the walls and roof, then free up the TBM so it could get on with its work.
It was science and technology against the elements, which are often really against you.
The result? A 3-month interruption of work on this stretch at an extra cost of several $1 million.
Incidents like that are a disaster for a construction site because you lose a lot of time. You risk not meeting the deadline, and it's very costly.
Unforeseen incidents like this were testing and exhausting for the crews who were already working around the clock, 7 days a week, in particularly harsh conditions. Contrary to preconceived ideas, the temperature is far from cool and far from constant under several thousand meters of rock.
There's a very simple law of physics. When there's pressure, temperature rises. So when you're in the heart of the mountain with thousands and thousands of tons of rock pushing down from above you, the rock gets very hot. When you touch it, it's at 50 degrees.
So one of the challenges we had to meet was to install a ventilation and cooling system to guarantee good air quality with temperature and humidity levels that were bearable.
On-site safety was a crucial point. The maximum temperature should not have risen above 28 degrees. And the levels of carbon monoxide and several other gases were constantly monitored.
Thanks to all these technical and technological innovations, the boring of the two tubes continued at an average rate of 15 meters a day. The construction site of the century, as it was called by the media, was about to enter its crucial stage. The 1,800 workers and technicians who had been boring through the mountain for 14 years would soon realize what kind of feat they had accomplished. The big day was set for October 15th, 2010. In a few moments before the expecting eyes of the teams, the two eastern stretches are finally about to be joined. The whole gallery shakes. The TBM is close, when suddenly, it's done. The two sections have finally become a single tube. An immense moment of pride and joy for the thousands of men and women who had been working for over 8 years deep in the entrails of the São Gotardo Massif. They'd just written a new page in the history of mankind.
It was incredibly emotional for the whole team. They felt they'd defeated the mountain. They'd been incredible, and they were experiencing something extraordinary, unforgettable. Huge emotions for all on the team, and a great victory for science and technology.
5 months later, and it was the turn of the western tube. Both rail traffic directions were now open.
Then we could finally announce it. We've done it. The 57-kilometer tunnel under the Alps has become a reality.
Construction workers, foremen, and engineers had all just accomplished a feat unprecedented anywhere on Earth. Remember, the accepted margin of error for each section was a tiny 25 centimeters. On arrival, the discrepancy was a mere 13.8 centimeters. A level of precision on such a mammoth work of engineering that's hard to believe. But work was far from complete. Once the two tubes were joined, another challenge began.
The aim of this project wasn't to drill some holes through a mountain just to prove it was possible. It was to build a railway and put it into service.
While constructing a rail line in the open air seems like child's play, doing it inside a tunnel is a wholly different ballgame. And once again, the difficulties were directly proportional to the scale of the work. The longer the tunnel, the more expensive it is, and the greater the number of risks of malfunctions. And to make things even harder, the narrowness of the tubes also generated specific problems, such as laying 2,300 kilometers of cables, which equip the tunnel right into the heart of the mountain.
We were in a single-track tunnel, so vehicles couldn't turn around to change direction. So we had to adapt the laying method. And the vehicles transporting the cables were fitted with cabs at both ends, so that they could switch and reverse in both directions.
The laying of the track for the future trains also required a whole host of innovations, without which the project would never have been achievable.
Another major enemy in a tunnel is dust. Outdoors, the wind disperses it. But in a tunnel, you need to make sure there's as little dust as possible.
Like water, dust gets in everywhere and acts like sandpaper on all the connections and fixtures that rub together, not to mention safety problems linked to the lack of visibility.
No one likes dust in their own home. It's the same in the Gotthard base tunnel, where we try to minimize dust.
Ballast, the crushed stone laid between the tracks to bear the load of trains, produces a surprising amount of dust. So they had to find a solution for such a long tunnel.
The solution? To set the track on a huge concrete slab running the full length of each tube. A very tricky operation that required careful orchestration.
This too was another innovation. It had never been done over such a length, replacing crushed stone with concrete.
Step 1. To lay, then weld 120-meter-long rails, advancing at over 2 kilometers a day.
It's crucial to ensure the gauge between the rails remains constant, otherwise there's a risk of derailing, especially at speeds of over 200 kilometers per hour.
These large concrete blocks that you see on the ground ensure the correct gauge is maintained. Once girdled by the concrete slab, they are completely unshiftable and guarantee the stability of the track. Step 2 consisted in casting the slab. This is the most complex part of the operation. To be effective, the concrete must be totally homogeneous so as to form a single block. an amazing feat over 57 kilometers, achieved thanks to this machine. Fed by a pump which supplies up to 5 cubic meters at a time, it can cast up to 200 meters a day. The concrete cast the day before didn't have time to dry before feeding in the concrete the next day, which ensured an ideal mix and maximum strength.
This is all part of railway technology, and it's crucial as it allows the track to go into service.
And finally, step 3. The installation of the overhead line which supplies the locomotive and hence the rest of the train with electricity. On a normal line, the current transported by the cable itself is enough to supply the necessary charge to pull a passenger or freight train. But in a tunnel as long as the Gotthard base tunnels, it's much too dangerous.
You can't supply the tunnel through a single point, especially as it could malfunction. So you need supplies to be delivered at various different points.
Because a power cut could have disastrous consequences, like blocking a line for several hours. To prevent this, the project designers built 5 mountainside power stations, the only way to avoid a power cut.
A construction site as big as this consumes as much energy as an average-sized town. That meant they needed to build power stations specifically for the site.
While a power cut was the biggest fear of those running this vast site, it wasn't the worst disaster to threaten the tunnel.
The biggest danger that threatens a tunnel as long as this, and it's a constant threat, is fire. Remember the Mont Blanc tunnel disaster? 39 people died simply due to a lack of ventilation. It's a constant threat.
Imagine what would happen if such a disaster struck a passenger train blocked beneath the São Gotardo Massif, 20 or 30 kilometers from the nearest exit.
Obviously, if we were unable to evacuate the passengers as quickly as possible, the results would be catastrophic.
This terrifying scenario is the worst nightmare of the firemen posted at the 2 extremities of the tunnel. They're on red alert 24/7.
A fire in a tunnel is extremely dangerous because temperatures rise very quickly. We have a training center where we can simulate a tunnel fire. We've experimented with several different techniques, and with the specialists, we've come up with the correct intervention procedures.
To counter such an eventuality, the on-site firemen have state-of-the-art equipment, like this ultra-sophisticated train capable of resisting flames in order to save lives. It can project a wall of water in front of it to fight against infernal temperatures. Its thermal cameras allow the firemen to see in total darkness. And finally, the cabin is completely fireproof and gas-proof.
If we firemen want to rescue people in danger, we have to consider our own safety also, our own protection.
But how do you fight your way through the flames to save hundreds of passengers trapped in such a long, narrow space? To find out, there's only one way: simulation. Imagine a suitcase catching fire on a train halfway through the tunnel. The train can't reverse, and the fire could grow to dramatic proportions before the train reaches the end of the tunnel. The only option is to reach one of the 2 intermediary stations specifically designed to counter such a danger. They're called multifunctional stations. Their presence in such a long and deep tunnel is a world first.
And in this multifunctional station, the train stops. The people are escaping themselves. They are going to the side of the multifunctional station, and then they walk on the other side to the other multifunctional station.
In the other tube, a train traveling in the opposite direction has been warned. It's come to a halt, and is waiting the passengers from the other train, who are all saved. But you need to be able to reach the other tube. Plus, in such a confined space, smoke spreads very quickly, and the risk of asphyxiation is very high. The passengers must imperatively get out of the tunnel in under 90 minutes. These famous multifunctional stations house what could be called the lungs of the tunnel.
The ventilation system has two functions. One, to supply oxygen to any people who are trapped, and two, in the case of a fire, to evacuate toxic fumes.
The huge ventilators installed in the villages of Cédran and Faido are the most powerful ever built.
Each of them has 1.4 megawatt. So in total, we have roughly 15.6 megawatt of installed power for ventilation, and this is roughly 25 times a Formula One racing car, so this is really much.
This phenomenal power of extraction is the best guarantee against the deadly risk posed by the toxic fumes produced by a fire.
We suck out the smoke above the train, out of the tunnel. We are talking about 200 cubic meters per second, roughly, which is pressed to the multifunctional stations.
But the best way to fight against malfunctions and fire is, of course, to prevent them. And that means anticipation. That's why if the slightest anomaly is detected before a train enters the tunnel, it's imperative to be able to divert it at the last second.
We have implemented a so-called level entry and a tunnel entry control. If it fits, it is led into the tunnel. Otherwise, it will be redirected to go over the old mountain track, which is still existing.
When a train enters the tunnel, our main concern is that it will come out the other end. So before it enters the tunnel, we check that everything on board is working, that there are no defective axles, etc.
When an axle is defective, it heats up very quickly. The heat is then detected by what's known as a heat box, positioned upstream of the entrances in both directions. These heat boxes are linked to an entirely automated safety system developed by a French multinational. Automation is essential to traveling at 200 kilometers per hour in such a narrow tube. To guarantee maximum safety, all trains that take the Gotthard-based tunnel are equipped with ultra-modern technology called ETCS Level 2. This complicated name masks the most innovative train control system in the world. Here, signaling is no longer displayed on the outside, but inside, directly on the driver's dashboard.
When you're driving your car, you read signs through your windscreen. When traveling at 200 kilometers per hour, the train driver might not spot a signal, so the idea is simple. Signs are displayed directly on the dashboard.
Drivers receive a speed reference which they must stick to, and they have no need to look outside of the cab. They could practically pull the curtains and drive with the instruments alone, a bit like with the automatic pilot on a plane.
The other interest in this cutting-edge technology is that it allows controllers to know exactly where the train is. As a GPS system doesn't work under several kilometers of rock, every locomotive is equipped with a beacon that transmits data from the rolling train to other beacons spread along the track.
From time to time, the train is passing so-called balises, which you can see on the track, some yellow blocks, which are installed there, containing very detailed information about the positioning.
The data gathered is immediately transmitted to a powerful software which analyzes it in real time. It's this software that determines, for example, the speed of the trains and the necessary distance between two trains in order to prevent a crash.
A train weighs thousands of tons and takes a long time to stop. So you need to know the exact distance to impose between the trains and which trains travel at which speed.
It's here in this huge command post installed in the village of Pelleggio that all this data is gathered. The center was specifically designed to control each millimeter of the tunnel. 50 people work in teams round the clock behind their screens, checking for the slightest anomaly. They're the guardian angels of Gotthard.
We're the eyes of the tunnel, and this is our command post. Anything that happens inside, we detect it immediately.
The slightest alert is quickly relayed, so it can be dealt with in record time.
There's a mechanical fault. Okay, I understand. So one's working, but not the other one. Okay, thanks for the info.
What's going on?
They've just noticed in the tunnel that one of the current converters is faulty. But although it's not working, the system is guaranteed to keep on functioning.
Okay, so there's no overlap.
That's right, no overlap.
Overlap means the systematic backup of electrical current feeds and transmitters, just like in a modern airplane. It's the best way of reducing the risk of malfunctions. The system is very effective for preventing accidents and incidents, but the command post still needs to react fast if there is one.
At the moment, one of the converters is damaged, so the repair team has to intervene as quickly as possible. Because if the problem leads to another, some installations will have no electricity at all.
Thanks to the overlap system and the reactivity of the teams, the safety of the trains is assured. For a gigantic engineering work like the Gotthard-based tunnel, the designers must anticipate everything, even the most unlikely incident. Imagine a total power cut blocking a train inside the tunnel. In such a case, traffic would immediately be stopped upstream of the tubes. All the other trains would be prevented from entering the tunnel to avoid it crashing into the train at a standstill. In such a confined space, a scenario like this would undoubtedly result in the worst railway disaster of all time.
In a tunnel like this one, an all-out power cut presents the greatest risk. We hope it will never happen. If everything's working well, we don't really have much to do. But if a serious problem were to arise, involving passengers, we'd be faced with a huge challenge. But we've prepared for that, and we're ready to rise to the challenge if need be.
Envisaging all possible scenarios, even the most unlikely, is therefore an obligation before inaugurating such a monumental tunnel. In the same way that airplanes are stretched to their limits before entering service, the Gotthard-based tunnel had to be put through a final series of tests in extreme conditions before being opened to traffic. One example is the speed test. Although trains would travel no faster than 200 kilometers per hour, tests were carried out at the record speed of 275 kilometers per hour. At this speed, the risk of an accident increases because inside a tunnel, the faster a train goes, the more violently it displaces the air mass, which provokes winds so strong they're comparable to those of a tornado.
We measured wind speeds around the train which were even faster than the train itself. For example, if a train was traveling at 200 kilometers per hour, at some points in the tunnel, we measured a wind speed of 350 kilometers per hour.
Winds as violent as that could tear down all the overhead lines. Having verified that the structures were able to resist a train passing at 275 kilometers per hour, the engineers could be certain that there'd be no problems at only 200 kilometers per hour. The Gotthard-based tunnel is so long that the winds give rise to an extraordinary sound phenomena. As a train moves through the tube, it acts like a piston of an organ. We were able to enter the tunnel on foot to give you an exclusive listen to the sound produced by a passing train.
The train is approaching now at high speed. It will pass very quickly. It's a passenger train that'll pass at 200 kilometers per hour, and you can hear that organ-like sound. We call it the Gotthard organ.
The passing of high-speed trains was also used to measure the changes in pressure passengers would experience inside the cars. It mustn't go above a level that could harm the human ear.
We have to take into account the aerodynamic effects for passenger comfort reasons. We can't have any sharp variations in air pressure. Otherwise, it will affect their hearing and cause discomfort to their ears.
These tests were the last step before the tunnel entered service. They concluded 25 years of hard work after the decision to cross the Alps underground was taken. The dream of the 20th century engineers has finally come true. The longest tunnel ever constructed by man is about to enter into history.
When you enter the tunnel at 260 kilometers per hour and come out 50 minutes later, it can be snowing in the north and sunny in the south. That's when you realize it's as if we've demolished the Alps. We've created a rapid junction which will now be used for at least 100 years.
The official inauguration of the Gotthard Base Tunnel takes place on June 1st, 2016. The event matches this technical and technological feat. The longest tunnel in the world is ready to meet the challenge of becoming the busiest rail access in Europe. Engineers, team leaders, construction workers, representatives of all the companies involved in the venture, but also rail enthusiasts from the four corners of the continent, several thousand people have gathered to celebrate the entering into service of the Gotthard Base Tunnel. To mark the importance of this event, several European heads of state are also in attendance. German Chancellor Angela Merkel, French President François Hollande, and Italian Prime Minister Matteo Renzi. They will have the honor of crossing the Alps for the first time through the record-breaking tunnel that will change the face of European rail transport.
Ladies and gentlemen, we'll soon be entering the Gotthard Base Tunnel. At 57 kilometers long, this rail tunnel is the longest in the world. Our passage will take about 20 minutes. If you have any questions, please ask the onboard crew members. Thank you.
Inside the train, all the guests of honor invited for this first passage know that they're taking part in a historical moment.
Thank you, Switzerland, for your hard work. It's a fantastic job, as you realize when you're traveling through the tunnel.
After this first passage, the then French president was also keen to show his admiration for the work accomplished.
La France, qui a toujours pour les grands ouvrages technologiques une admiration, aujourd'hui, et c'est rare, s'incline devant la Suisse.
From the start of the works in 1996 and its inauguration 20 years later, this insane project broke all records. An outsized performance made possible by the hard work of 6,000 determined men and women, aided by revolutionary machines.
Without the huge TBMs, all the cutting-edge technology, all the skills and know-how united in this project, they would never have been able to meet the deadline for this 57-kilometer tunnel beneath the Alps. It's a real feat.
It's one of the safest tunnels in the world, because it's one of the most recent, and because it's an exceptional work of engineering.
A work of engineering thought up and designed by enthusiasts, the professionals of underground construction sites, and railway engineers.
When you find yourself, as I did, 35 kilometers from the Northern Gate, with 2,350 meters of rock above your head. It's 35 degrees. You're all alone. It's as if you can feel the pulses of the mountain. It's a magical place and a unique moment, and one that you'll probably experience only once in your life.
We're now extremely proud to say to everyone, to all Europe, that we have succeeded in meeting a massive challenge and that this is a victory for everyone.
In a way, the Gotthard-based tunnel has made one of the prophecies of the French novelist Jules Verne come true. Man truly has journeyed to the center of the earth.